Hello, and welcome to part 2 of this Math 142, this Calc 2 Gateway to Practice video. We have 3 problems left here. We worked through these problems 1 through 3 in the first video, and now we are going to work on problems 4, 5, and 6. So what I've done here is I just kind of pulled up a random Gateway practice exam and am working through the problems in real time. Okay. So this is problem 4 that we have. We have the integral from negative pi to pi of x times sine of x over 5 dx. Okay. So my thought here is to use integration by parts. And in particular, so what am I going to choose to be my du? What am I going to choose, or what am I going to choose to be my u and my dv? Well, that is a great question. I'm so glad that you asked. There's a couple of choices that we could make here. So first, I'll just go ahead and write down my symbols that I'm going to need. So the two choices basically are I have x and I have sine of x over 5, right? I have these two pieces. One of those is going to have to be my u, and one of them is going to have to be my dv. I am going to choose x to be my u, and that is because I know that if I take the derivative of x, I just get a constant. The derivative of x is just 1, right? So I get a constant, and that's going to be super nice in a couple of minutes whenever we go, because remember, so what we're going to have in the end is we're going to get uv minus the integral of v du. No, I don't need to see my face. Okay, I need to see my notability. There we go. So the integral, right? So we're going to have uv minus the integral of v du. That's what we're going to have here in just a moment. And so if this du is just a constant, if it's just, in this case, 1 dx, that's probably going to make our lives a whole lot easier. So whenever we can get our du to be a constant, that's usually a really good thing. So that's what I'm going to try here. That means that my dv is going to be sine of x over 5 dx. So my v, well, the antiderivative of sine is negative cosine. So I'm going to have x over 5, and I'm going to need to multiply this by 5 because of this x over 5. So in sum, we get negative 5 cos x over 5. If you want a little bit more explanation of why we're multiplying by 5 here, I talked about this more in part 1. So this problem up here, where we had the antiderivative of cosine of 2z. So if you want to go back and watch that to get a more detailed explanation, I might recommend that. In short, when I take the derivative of sine of x over 5, I'm going to need to divide by 5. I'm going to need to multiply by a fifth because of this x over 5 on the inside. So when I anti-differentiate, when I do the opposite, rather than dividing by 5, I'm going to need to multiply by 5. In other words, rather than multiplying by a fifth, I need to divide by a fifth, which is the same as multiplying by 5. So again, see part 1 for a bit more explanation on where that is coming from. At this point, we have all of our ingredients, so we can go ahead and use our handy dandy integration by parts formula. So first, we're going to have uv. So uv is going to be x times negative 5 cos of x over 5. And we're going to evaluate all of this from negative pi to pi, because those are our original bounds up here in our original integral, minus the integral from negative pi to pi, right? So we're keeping those bounds here, of v du. So v du is going to be this negative 5 cos x over 5 dx. And then our so our du is this dx here. Okay, so going to the next line, if I plug in x equals pi, then I'm going to get pi times, so I'm going to get, I'll get negative 5 pi cosine of pi over 5 minus, now I'm going to plug in negative pi. So I get negative 5 times negative pi. This is going to get a little messy, but we'll come back and simplify things in just a moment here. Cosine of negative pi over 5. Okay. So that's the first part. Again, we'll come back and simplify that in just a moment. Then over here, for the second part, we get plus. I'm going to go ahead and take these two negatives and make them a positive. And I'm going to go ahead and take this 5 out front of the integral. So I'm going to end up with plus 5 times the integral from minus pi to pi of cos x over 5. Yes, which I'll come back to. Okay. Now, let's look at this first part again. Let's clean things up a little bit. So I get minus 5 pi cos pi over 5. And then I'm going to get what? Plus, there's a, oh boy, there's a triple negative here, I think. Yeah, there's a triple negative. So we'll get minus 5 pi cos minus pi over 5. Okay. Now that minus pi over 5, I would love to simplify. I'd love to just say what that is, but that's not one that I know off the top of my head. That's not one of the nice ones that we're supposed to have memorized. So I'm just going to leave it as cosine of pi over 5, negative pi over 5. So I'm just going to leave those alone. Coming over here to our integral. Okay, this is going to go back to what we talked about up here whenever we did the antiderivative of sine of x over 5. The antiderivative of cosine is sine. So 5 times. Now the antiderivative of cosine is sine. So we get sine of x over 5. But then just like we needed to multiply by 5 up here, we need to do the same thing here. So that becomes 5 sine of x over 5. And we're going to evaluate this as well from minus pi to pi. Okay, this stuff over here, I'm just going to copy. So we'll deal with this stuff in just a minute because I think we might get some, we're going to get some interesting stuff here in just a moment. Now over here, I get plus 5, and now, so if I plug, I see, okay. So if I plug pi in for x over here, then I'll get 5 times 5 sine pi over 5. Sine pi over 5 minus 5 sine negative pi over 5. Okay. Now, here is where I'm going to use a couple of key facts about these, about sine and cosine. So first I'm going to say, so first, cosine of negative theta, I claim is equal to cosine of theta. And here's why. So this is, in other words, cosine is an odd function. Let me explain this real quick. If we think about the unit circle, right? So, I mean, maybe just for example, if I do like, so let's say that I go, if I go theta radian, so if I start here and I go theta radians in this direction, maybe that takes me here. So let's just say that this angle here, let's say that if I go from here to here, let's call this theta. Right, and let me use a different color maybe to emphasize that, right? Now, on the other hand, if I go negative theta radians, that'll take me here, right? And notice that the x coordinates of these 2 points are the same. And remember that cosine is just the x coordinate whenever we play this game, right? Whenever we start at 1, 0 and rotate. So that explains this first identity. Similarly, sine of negative theta, well, let's think about it. So if we look at this picture again, I'm going to go and put this picture in the middle of these two. If I look at this picture again, well, the y values aren't the same, right? The y values of these 2 points are different. In fact, they're just negatives of each other. So sine of negative theta is the negative of sine of theta, right? Because the y values, these are negatives of one another. So that's where these facts are coming from. So all of this is to say that I can replace, so like cosine of negative pi over 5, I can replace with just cosine of pi over 5. So I get minus 5 pi cos of pi over 5. I admit I don't know how much of this part the gateway will require you to do, but it is going to make things simpler, which is why I think it might want this. Although I admit I'm not entirely sure. Okay, so I can replace this cosine of negative pi over 5, which is cosine of pi over 5. Maybe I'll underline this so you can see this change that I'm making. Okay, and I'll underline that in orange so you can see. On the other hand, I can replace this sine of negative 5 sine of negative pi over 5. We'll see. Okay, so here, so I get plus 25 sine of pi over 5. And now I would get minus 25 sine of negative pi over 5. However, if I replace this sine of negative pi over 5 with negative, right? If I make this substitution, then what we end up with is we actually end up with a plus 25 sine pi over 5. Okay. Right, so that's because of this substitution, right? So I'm making this substitution here in place of sine of negative pi over 5. So all of this comes out to negative 10 pi cos pi over 5 plus 50 sine of pi over 5. And that would be our final answer. Again, I don't know what sine and cosine of pi over 5 are, so I'm just going to leave them like that. That's the most precise answer that we can give. Okay, so again, kind of big picture idea here. We wanted to do this integration by parts, and what I noticed was, hey, if I make my u x, then when I take du, I'm just going to get a constant, which is super nice. And that's what kind of facilitated this whole thing. Then we used these trig identities. So in other words, so this first one says that cosine of theta is an odd function. That's, excuse me, an even function. I said odd. This whole time I meant even. Goodness. And then over here, sine is an odd function. And so that's how I did a little bit of simplifying here. Again, I don't know how much the gateway is going to make you do that kind of simplification. But okay, problem 5. We have the antiderivative of 7 to the x dx. Okay. So I think for this one, it's going to be important for us to recall that the derivative of 7 to the, so if I take the derivative of 7 to the x, what do I get? I get 7 to the x times ln of 7. So let's go back up here for a moment. Whenever we took the antiderivative of sine of x over 5, we said, okay, if I was taking the derivative of sine of x over 5, I would need to multiply by 1/5. Therefore, when I take the antiderivative of sine of x over 5, I must divide by 1/5, or in other words, I must multiply by 5. So let's come back down here. When I take the derivative of 7 to the x, I must multiply by ln of 7. Therefore, when I take the antiderivative of 7 to the x, I must divide by ln of 7. It's that same idea, okay? So really, that's all we need for this one. And in fact, so to check ourselves, if I take the derivative of this 7 to the x over ln of 7, well, that one of right, we kind of just have this 1 over ln of 7 sitting out front is a constant. And then the derivative of ln and then the derivative of 7 to the x is 7 to the x times ln of 7. And so why did we divide by this ln of 7 here? We divided by it because now when we take the derivative of this thing, it's going to cancel out with that ln of 7 that we just got and give us that 7 to the x. Okay, so basically we need to divide by this ln of 7 to kind of like cancel out with the ln of 7 that you would multiply by when differentiating. I hope that makes a bit of intuitive sense. There is a way that you could do this maybe a bit more rigorously using a u substitution, but it would get rather complicated. And so I think it's worthwhile in this case to kind of understand this intuitive idea. I think that will perhaps be helpful. Okay, and I should note the reason that this works is because this ln of 7 here is just a constant. Whenever it's whenever we're doing like product rule type things, it gets a little bit hairier. It doesn't work quite this nicely. But whenever we just have constants like this ln of 7 or like the 1/5 that we were looking at up here, things are relatively nice to work with, and you can kind of think through it in this way. Okay. This final problem is a partial fractions problem. 2x squared plus 17x plus 195 all over x cubed plus 2x squared minus 29x minus 30 dx. Okay. Your first thought here might be one thing that I thought about when I saw a similar problem yesterday. One idea might be to try polynomial long division. However, the issue with that is that the degree of the top is smaller than the degree of the bottom. So polynomial long division isn't really going to go anywhere. You would use polynomial long division whenever you have something with a bigger degree on top than what you have on the bottom. For example, if we think about like with numbers, and I'm going to erase this in just a second, but like with numbers, if we have like 17 over 5, then we can break this up as 3 plus 2/5. On the other hand, if I have like just 4 over 5, there's not like, and I try and like break it up like this, there's not really anything that we can do because that 4 is already smaller than 5. And it's kind of the same idea with polynomial long division. Because the degree of the top is already smaller, that's not really going to get us anywhere. Now, this certainly looks like a partial fractions problem. And the issue with, I shouldn't say issue maybe, but the first step then is going to be to factor the denominator. Now, I admit I had to I had to remind myself of a strategy for doing this, but fortunately I was reminded of such a strategy. So a strategy for factoring this cubic. For me, that my first thought is to factor by grouping, because we have 4 terms. However, that's not actually going to get us very far here. Okay, if we try and factor by grouping, I can take an x squared out of both of these, and then I'll have an x plus 2. But there's no way I'm going to get an x plus 2 by factoring anything out of this 29x minus 30, right? So unfortunately, I don't think that grouping is going to work here. Another strategy, which I was reminded of, is another strategy for this. So the maybe key idea is that x minus a is a factor of the polynomial f of x if and only if plugging in a gives us 0. In other words, if and only if a is a root of f. So what does this mean? This means that if we know a factor of f, right? If we know a root of f, we know a root of this denominator, then we could use that to help us factor because we would know what one of the factors has to be. For example, if it turns out that 3 is a root of this denominator, then we would know that x minus 3 has to be one of our factors, and we could go from there. To help us with this, I was reminded of the rational root test. Okay, so the rational root test, which I have pulled up in another tab just to remind myself a bit, because it's been a minute since I've looked at it. This tells us that any rational roots of this polynomial, so net rational roots of this denominator plus 2x squared minus 29x minus 30 have the form roots or factor, excuse me, or divisor of 30 divided by divisor of 1. Okay, so 1, what is this 1? This 1, or excuse me, where's this 30 coming from? That's the constant, right? That's the constant at the end here. Technically, it's minus 30, but either way works just fine. And this 1, that is the x cubed coefficient. Okay, so what this allows us to do is it allows us to search for some factors. So for example, what about x equals 1? Is x equal, so divisors of 30. Okay, so I have plus or minus 1. So if I plug in a 1, do I get 0? Plug in a 1, I certainly do not get 0. So that one's not going to work. I'm going to put an x through it. 1, put an x through it. We have minus 1. That's not going to work either. I'm going to cross that one out. What else do we have? We also have 2. 2 is a root of 30. So I get, if I plug that in, I get 8 plus 2 times 4 is 8. So again, I get 16. Yeah, that's not going to work. Minus 2 isn't going to work either, right? So I'm going to get negative 8 plus 8 is 0. Yeah, that's not going to work. What about 3? So I plug in 3, I get 27 plus 2 times 9 is 18. So 27 plus 18 is 45. Yeah, that's not going to work. What about minus 3? That one, so I get negative 27. I have a good feeling about this one. So I have negative 27. So what I'm doing is I'm just plugging this into that denominator. So I get negative 27. Negative 3 squared is 9 times 2 is 18. So plus 18 plus 87 minus 30. So what do I get? I don't think it's going to work. No, it's definitely not going to work. Right, so we keep trying things. X equals 5. So if I plug in x equals 5, what do I get? I get 125 plus 50. Ooh. Okay, this is good. So if I plug in x equals 5, then I'm going to get 125 plus 2 times 25 is 50. 29 times 5 is 145. 1 is 145. And then minus 30. And I do get 0 here. Okay. So 5 is a root. Maybe another thing that I'll point out, and actually this is probably a lot easier. Another idea. So now I found a root. Another idea for finding a root is you could probably just graph this thing. Right? So I'm not going to do this. I'm not going to show this here. But you could totally look at the graph, right? And so what I know about this graph now, I'm just going to do a very rough sketch, but I know that this graph has to cross at x equals 5. So if you graph this and you look at where it crosses the x-axis, that'll also tell you a root. probably a little bit more quickly than this. So that's probably the way to go, actually. But here's the idea now. So I know that one of the factors is x minus 5. How do I figure out what the other factors are? Well, I'm going to have to divide, and have to do my polynomial long division, right? So we're not going to totally get away from polynomial long division. Minus 29x minus 30. I'm going to divide, right? So 5 is a root. So this tells me that x minus 5 is a factor. So if I do this long division, so what do I multiply x by to get x cubed? I multiply it by x squared. So now multiply the x squared by x minus 5, and I get x cubed minus 5x squared. Subtract. Hopefully this algorithm will look familiar. I get 7x squared minus 29x minus 30. Okay. Now I multiply x by 7x to get 7x squared. Minus 7x squared minus 35x. And I get 6x minus 30. Write it over here. 6x minus 30. And now plus 6. Okay, so plus 6, and I get 6x minus 30. And what do you know? I get 0. So I get a remainder of 0. So this tells me, what does this tell me? This tells me that this denominator, x cubed, so therefore, x cubed plus 2x squared minus 29x minus 30 is equal to x minus 5 times x squared plus 7x plus 6. And now you can check that this becomes x plus 6 times x plus 1. Okay. So then I just factored this polynomial. Maybe another thing I'll add is that to find these roots, you could also graph. So maybe a better way of going about all of this. So maybe a better strategy might be to graph the thing, see that it has roots at x equals minus 1, minus 6, and 5. And the factors must be x plus 1, x plus 6, and x minus 5. Because this is a cubic polynomial, it can only have 3 roots, and so it can only factor into 3 terms like this, and 3 factors like this, and so that's what we get. In any case, however you do it, we have our factorization of the denominator. So we're not quite done yet. We're just getting started still, but that is our factorization. Now, what do we get? We have 2x squared. So now we're on to our partial fractions. We have 2x squared plus 17x plus 195 over this denominator, x plus 1, x plus 6, x minus 5 equals, okay, because each of these are just linear factors, we're just going to have A's, B's, and C's, right? We're just going to have one letter up top. We're not going to have like a CX plus D or anything like that. Okay, so if I multiply both sides by this denominator, then what do I get? I get 2x squared plus 17x plus 195 equals, okay, so if I multiply both sides by that denominator, when I look at this first fraction, this x plus 1 is going to cancel with this x plus 1, but then I'll still have the x plus 6 times x minus 5. Kind of similarly for the b, I'm going to have an x plus 1 and an x minus 5 here. And for the c, I will have x plus 1 times x plus 6. Now, there's multiple ways of going about solving for a, b, and c from here. The strategy that I'm going to use is I'm going to say, okay, if I plug in x equals -1, right, so if this equation is true, then it should be true for all values of x. That's what we want. If x is -1, well, I plug x equals -1 on the left-hand side, and what do I get? I get 2 minus 17 is -15, plus 195 is 180, equals, now if I plug -1 in on the right-hand side, I get a times -5 times -6, so I get 30a, and so I get that a is equal to 6, so 6 equals a. Oh, I should be more clear. By plugging in x equals -1, if I plug x equals -1 into here, this x plus 1, that goes to 0, which is why all of this goes away. Similarly, if I plug x equals -1 into this goes away. So that's why I only looked at this first part here. Okay. So I chose strategically a value of x that I knew would kill these two terms, so I could just focus on the a's. Similarly, if I plug in x equals 5, then what's going to happen, this first term is going to get killed, and so is the second one, because they both have a factor of x minus 5 in them. By plugging in x equals 5, what do I get? On the left, I get 2 times 25 is 50, plus 85 is 135, plus 195 is going to give me 330. What do I get on the right-hand side? Well, like I said, the first two get killed. The third one becomes c times 6 times 11, so I get 66c. And if I divide both sides by 66, I find that c is equal to 5. And finally, if I plug in x equals -6, then the a and c guys will get killed, and I'm just going to be left with the b. So on the left-hand side, what do I get? I get 72 minus 102 is -30, plus 195 is 165. And now the a and c parts get killed. I just have the b part, and I get -5 times -11, so I get 55b. So we get that b is equal to 3. Okay, so now I'm just going to be a little bit lazy here. Our original integral is equal to, right, so this partial fractions decomposition gives us, well, our a is 6, so we get 6 over x plus 1, plus b is 3, so 3 over x plus 6, plus c is 5, so I get 5 over x minus 5, all of that dx. And now, so let me just briefly, in the interest of time, because my Zoom meeting is running short, let me just briefly, in the interest of time, show how to do one of these integrals. So the integral of 6 over x plus 1 dx, right, well, that's the same as 6 times the integral of 1 over x plus 1 dx. If I let my u be x plus 1, then my du is just dx. Now, this becomes 6 times the integral of 1 over u du, and that integral is ln of u, ln of the absolute value of u. So we end up with 6 times ln of x, absolute value of x plus 1 plus c. So that's what that first integral comes out to, 6 times ln of absolute value of x plus 1. I'm going to go ahead and just stick 1 plus c at the end. And as you can probably see, these other integrals are going to work very similarly. And so what are we going to get? We're going to get plus 3 ln of x plus 6 plus 5 ln absolute value x minus 5. These are all absolute values. I'll stick my plus c at the end. Okay. So that took a little bit longer, I think, than hoped. Again, I want to emphasize, though, that probably a quicker way of doing all of this in retrospect would be to go ahead and try and graph this. And look for where it crosses the x-axis, right? So look for the roots, or look for the zeros, I'll say. Look for where it crosses the x-axis. If you get 3 x values, then that is going to tell you exactly how it has to factor, okay? If you want to do it this way, I'm more of an algebraic person myself. You can use the rational root test to try and find roots. Notice, right, so the divisors of 1 are just plus or minus 1, which is why I didn't have to worry about denominators up here. So what I did was I was checking for roots in this way, which we could have also done. Wait, I said that x equals -1 was not a root? Was that wrong? That must have been wrong. Oh, that was wrong. -1 was in fact a root. So actually, -1 is a root. That was silly of me. Fortunately, we were able to recover. Silly of me. But anyways, so you could graph, or you could use the rational root test to identify roots. And once you find one root, you can also do some of this. You can do this polynomial long division. Anyways, that is how I would go about this problem. I hope that you found this to be helpful, and good luck on Gateway 2.